My name is Gottfried Gooch. I would like to make a presentation about inertial propulsion. In particular, is inertial propulsion valid? Is it a valid science idea? And in the beginning, we have to look at the progression of the discoveries which led us to believe that it is not possible. To clarify what inertial propulsion is, we have to define inertial propulsion. Inertial propulsion is an isolated system which has a mass motion, internal mass motion, and it's usually a rotational motion combined with some kind of a linear reflection or linear motion. This internal action generates a impulse, a force over a time duration, which pushes this device forward without the benefit of traction or expulsion of masses. What is the progression of the discoveries which led us to believe that this is not possible? In the beginning, Galileo kicked this science off with a notch board experiment. And we see here the notch board experiment. A board, two boards, where notches are inscribed in equal intervals. And to operate this, a brass ball is being rolled down, and it makes a clicking pitch, and this clicking pitch is progressively higher and higher, meaning a shorter time interval between each notch. So this is Galileo's notch board experiment, and there was some math business involved. Galileo used a resolution to a word problem. He made this a word problem, and word problems takes a high discipline of thinking to wrap one's mind around it, and therefore it was difficult to understand. And so these fellows here, Leibniz and Huygens, came along, and they said, well, this is an old hat. It has to do with vis viva, which we experience when we throw stones at a rock wall, and it will demolish this rock wall, which workmen put all together, with many hours of work. So a rock can do a progressive amount of work the faster it flies. These were very accomplished people. Leibniz found a way of calculating pi more efficiently. Huygens invented the grandfather clock with a pendulum. Then we had Newton come along and said, I have an easy way to simplify this word problem, and I put this experiment, the Galileo's notch board experience, on a time basis, equal time-based intervals. Then this cumbersome problem here, where we have an exponential function, and we have an exponential function here. We have a uniform function where the force equals the mass of the brass ball times the acceleration. So it becomes an easy word problem, easy to understand, easy to work with, and the advantage is that the force is an average value over the acceleration time duration. So we can work with that. Newton associated all kinds of laws with this. He extrapolated, more laws for this, and that is because the time duration for this force, we can extrapolate the impulse, the force times the time duration, and the force times the time duration is the momentum. This mass s, it's velocity times the mass. So momentum is in Newtonian physics very important. It's a conserved quantity that within an isolated system in a linear reflection, you cannot escape it. You have to always have some kind of a collision or interference in an isolated system. You cannot escape it. It will be always, stay within this isolated system. So in Newtonian mechanics, we cannot visualize this to be true, that inertial propulsion actually exists. Then technology progresses, and James Watt builds a steam engine, and we are converting coal to mass motion, and we move objects and people with machines. Now there appears to be a problem with Newton's formula. There's no built-in cause and effect. The steam engine has an easy cause and effect. We burn coal, this is energy, and we convert this energy to mass motion. Here, we do not really describe what causes this force in the first place. So here we solve this, the cause and effect, and we do very accurate measurements. Mr. Carolus makes a very accurate measurements. And we say that the energy we have to put in is 1/2 times the mass times the velocity squared. This goes back to now a little bit to Leibniz. He wrote a book about calculus, which defined the exponent rule, how to get the averages out of these progressive kind of behaviors. And this here 1/2 says this is a uniform acceleration. This within a uniform acceleration, this holds true. There are premonitions that what happens is non-uniform, and so we still can give credit to Newton if we manipulate this formula, force times mass and acceleration, and multiply both sides with the displacement of this force. Then we end up with Thomson's energy formula. However, we have to now question what is happening. Is it a uniform acceleration, or is it a non-uniform kind of a curve? And then we have to distinguish that and know that. And but to be valid, for the steam engine, we have to be in uniform acceleration. Then this Mr. Hamilton comes along and says there's another aspect of conservation here in an isolated system of a steam locomotive with a load of energy behind it in the coal tender. We have the sum of the potential energy of the coal tender and the acquired kinetic energy of that steam engine is a constant sum. It doesn't change. We cannot gain electricity or lose it or anything like that. It's a rock bottom, foundation of our science. Then this Heinrich Hertz comes along and says, we're doing wonderful things in electrodynamics where we, this fellow Heinrich Hertz, he already had premonitions and proven this in a laboratory about radio communications and radar, would you believe? So he did this with, electromagnetic devices which generated very large sparks. And he did other experiments with rotating, electromagnetic fields, and he experienced some strange things happen there, which relates to a mathematician, Gauss. Gauss analyzed rotational system. He says, if I analyze this, I predict there is, imaginary numbers in the system, literally like we're seeing ghosts here. And this is what Hertz was working with. One of the most prominent aspect of this is that in a generating system, alternate current system, where the generator in the generator house has to do more, supply more power than you get in your furnace motor, blowing hot air. So there is a difference. There is apparent larger power, being put into this generator, and less power appearing at the furnace motor, shaft. And the difference between the two we call the power factor. So Hertz worked with these machines which could do, sparks, and that's another aspect of Gauss's imaginary numbers. It is an avalanche system where suddenly we have a discharge, and you see this in old scary movie, where they have these arc arresters, and make you believe that they bring people back to life with with electricity. So here we are. Hertz says, I'm going to write a book, and I'm going to put all these principles on an energy footing, and have create symmetry in all these fields. And he came up with a formula, and the symmetry formula is that energy is equal to impulse, Newton's impulse squared, divided by 2 times the mass. This also, somewhat indicates there is an avalanche possible when the impulse happens at a very short time. We are going to have very large forces generated. In the other aspect, you can expect a very large energy output for an impulse, because it's a squared relationship. So we predict this here, and Hertz wrote a book, and Newton wrote a book, and Leibniz built a book about calculus. So these disciplines are very well understood now. We have to look at Newtonian, first of all, at Newton's Principia. And in Newton's Principia, Newton limits his validity of this because he has premonitions of this happening already, possible happening in electrodynamics. He wants to write the Pacific. He wants to present a workable word problem. We can,